We are the DWI, Leibnitz Institute for Interactive Materials in Aachen, and we work in close collaboration with RWTH Aachen University. As part of the Leibniz community, our job and our specialty is to accompany projects from the fundamental aspects of research until their applied stage. As we like to create matter and materials, our focus is mostly synthetic. Together with Symo-chem and biomaGUNE, DWI forms the synthetic basis of the EUSMI program, delivering the materials for our collaboration partners to investigate. For example, the soft matter analytics in the EUSMI program can find out better what the physico-chemical properties of these materials actually are. Additionally, the computational modeling of these materials can generalize the principles behind their construction. To our scientific as well as industry collaborators, we are offering a big toolbox of water-soluble building blocks for the construction of materials. Specifically important for us is the upscaling of these building blocks. In addition, we are offering the possibility for other institutes to send their researchers here to DWI so that they can receive training in synthetic methodology. Currently, transfer of the materials developed at DWI to industry is inhibited by their high cost. To facilitate market transfer, we are actively improving synthesis pathways to be higher yielding and less costly. Our scientific task within the EUSMI program is the design and synthesis of dynamic microgels that can then be equipped with gold nanoparticles, allowing them to undergo photothermal heating by plasmonic effects. With this, we want to create microgels that are colloids, which means that they are microscopically suspended particles that can undergo hierarchical structuring in the same way that molecules form chemical bonds with each other.
Dr. Ahmed Mouran, a physicist at DWI, is working together with his research group on the development of artificial micro-swimmers.
Over the last year, we were busy fabricating and studying small, micrometer-sized objects that it can move actively in water. It moves in a way very similar to a living microorganism like bacteria. But actually, you may wonder why this is a problem, why it's difficult to fabricate objects that it moves like bacteria.
The way an object can move in a liquid is determined by the so-called Reynolds number, which is the ratio of the inertial force to the viscous frictional force acting on the object. Heavy objects like this toy frog can swim forward using symmetric strokes in clear water, a low viscous liquid, but it doesn't move an inch in glycerol, where the friction force is much larger than the inertial force. To go or not to go is a question of the Reynolds number. Under the microscope, we observe that very light objects, like bacteria or this synthetic hydrogel particle, experience a very low Reynolds number even in clear water. Therefore, symmetric mechanical movement doesn't push them forward.
To develop minuscule micro machines and micro objects that they are very small, able to move in water and even more difficult in biological fluids, which is the vision of this project, we need to solve two key issues. The first one is the chemistry and the material that it allows us to fabricate an object that it moves. It's not enough. The second one, that the direction of the motion can be controlled accurately.
Chemists at DWI are synthesizing polymetric material, which they cross-link by illuminating it with ultraviolet light in a micromold to control the shape of the final object. Additionally, the objects are loaded with gold nanoparticles, which will later help to bring energy to the particle, which is needed to make it move. The cross-linked material swells to a multifold of its original size by taking up water, forming a hydrogel which can be rapidly swollen and shrunk by small temperature changes. These changes can be induced by irradiating the embedded gold nanoparticles with red laser light. When the laser is on, the objects shrink slightly, but swell back to their original volume very rapidly once the laser is off. If the shape of the objects is properly selected, the swelling and shrinking cycles induce a movement that is asymmetric in time. Time asymmetric movement is actually the trick microorganisms use to swim at low Reynolds numbers. In this way, even these artificial objects are able to swim, which is a first step towards much more ambitious and challenging research goals.
Making a synthetic, very small object, micro-robot, that you can inject in the body, and it's able to do diagnostic, for instance, or even to deliver some medication and repair organs. It's a big vision, worldwide a problem and a challenge. We at the DWI, we did the first step where we took a very simple material, a hydrogel, and we make it small enough that it can move in water directionally. Toward the final goal, there is a long way to go.